Welcome everyone. So, in this module we are going to discuss about several RTL optimizations, specifically targeting improving speed of your design, how to improve your area of your designs, and improving power consumption of your design. Right? So, there are certain kind of RTL optimizations are there, and that can be applied in your design. So, so that your design have a better timing or say area or power, right. So, in these three or four modules we are going to discuss about all these things. Today the topic of our discussion is that RTL optimizations for speed. Okay. So, as I mentioned, so we are going to discuss about that several RTL optimization today's, and when you are talking about the speed of a design, there are three parameters come into picture. One is throughput, one is latency, and the next is timing. Okay. So, we are going to talk about, so speed is characterized by one of these three terminologies, and we are going to talk about all the optimizations that are targeting all these three, right. So, now let us discuss what is throughput. So, when you are talking about your design, what is the throughput? It is kind of amount of data that are processed per clock cycle, right. So, you are in every cycle some data input are coming and some output is coming out, right. So, it is basically the number of bits that are coming out of your design, that is called throughput. Okay. And what is latency? The latency is something the number of clock cycle is required to process your data, right. So, if you give some data at say time t, it might take some k cycles. So, after k cycle only that output will come into, will be available. So, it needs k number of cycles, right. So, that is the latency of your design. And the next is timing. So, timing is something is related to the combinational delay between two register, the maximum combinational delay between two registers. So, if suppose there is a register here and there is another register here and there are some logic circuits here, right. So, combinational logic and all some function units and all, there is no sequential elements here, and it needs some time, computational time to execute this, right. So, the delay between this register to this is called the combinational delay of that circuit, right. And your timing will be determined by the maximum of such delays, right. So, you have several pair of registers, right. So, there may be say 100 register in your design. So, there may be say 500, 600 path between any two registers, right. And between all possible path between two registers, maximum delay will determine the maximum computational time, that is called critical path of your design, right. So, this is very well known. So, so that is the logic delays between two sequential elements, and so this is basically, and your timing or the frequency that can your circuit will achieve will be determined by this factor, right. So, your maximum the clock period should be, so if this is your clock, so that clock period will be minimum that clock period will be minimum of that critical path delay, right. So, if say your clock period your clock period will be determined by like this. So, suppose your delay is set 10 milliseconds. So, you will get 1 by 10 millisecond, right. So, your clock period is 10 milliseconds. So, your clock period will give by seconds and frequency is 1 by clock period. So, that will give you say 100 megahertz, right, because this is 10 to the power 6. So, this is say microsecond, sorry. So, this is microsecond. So, this will get 100 megahertz, right. So, your clock period will be determined by this maximum combinational delay, right, and your objective will be maybe different. So, your objective may be you want to improve your throughput of your design, right. So, then you have to apply certain kind of techniques that will actually improve the throughput of your design, or you might try to improve the latency of your design, right. So, that you try to go get the result as soon as possible, right. So, number of cycles is less between this, and your objective may be improve the timing, right. So, it is basically high throughput, low latency, and timing also has to improve. That means, the computational delay or that critical path length has to be reduced. So, that is the overall objective, right. So, let us take an example to understand this fact. So, suppose this is my circuit, right. So, there is a combinational unit here. So, input is coming, some combinational circuits are here, then there is a registers, then there is another combinational circuit which process this data and output stored in these registers, and again this combinational unit, and then this final result is stored in this register, right. And say for uniformity, so my inputs are all 8 bit, all the data path which is 8 bits. So, what is the throughput of this design? So, once you give some input here, first we will discuss latency. So, it is so in the first clock it will come here, then the second clock this data will be processed, it will come here, and in the third clock this data will be processed and it will come at the output. So, you need 3 cycle, right. So, you need 3 cycle to give this input, so output will be generated for a given input, right. So, that means the latency is 3, right. So, it is basically the number of logic sequential register level from the input to output, right, and you can have multiple paths, right. So, from your input there may be multiple path. So, some path may be so suppose in this path there are maybe 2 registers, in this path maybe say 4 registers, right, there may be 4 registers, this path may be only 1 register. So, this latency will be determined by the maximum number of register in path from the input to output. So, this is the input and this is your output. So, for this path critical latency is 4, not 1 or 2, right. It is the maximum number of registers there between the input and output for any path from the input to output. Okay. So, for this circuit, since I have 3 level of registers, the latency is 3, and what is the throughput? So, 8 bit are coming out in every for this 3 bits, right. So, your throughput is something 8 bit per clock, right. So, basically, so what happened here? So, after 3 cycle your output will come, every cycle some output will come, right. So, this is something wrong. So, your throughput is basically here 8 bit per cycle, right. Why? Because once you give the first set of data here, so that will after 3 cycle the result will come, right, but in the second clock you give another set of input, right. So, that will be also processed. So, suppose you give here say A, so the result of A will come here after 1 clock, right. So, if you just write this clock 1, so you give A here. So, this is a register 1, so this is 1, 2, 3, right. So, in your register these are all 0. In clock 2 the A will come here and next input B will come, right. In clock 3, so A will come here, B will be processed here in these registers. This is register 1, this is register 2, this is register 3, and in some new input will come, right. So, after 3 clock this result will be available. In clock 4 again B will come here, C will come here, some new data will come, right. So, now after that every clock some output will be available, right. So, in clock 4 this clock 5 U will come, D will come here, C will be available, right. So, after that every clock your every clock you will get some output, right. So, that means your throughput is 8 bit per clock. Okay. And the timing is what? So, as I mentioned, this is the maximum combinational delay of any between 2 registers. So, here there are 3 set of combinational delays, it will be the maximum of combinational circuit 1, combinational circuit 2, or maximum maximum delay of these 3 circuit, right. So, for this circuit latency is 3, throughput is 8 bit per clock, because it is a parallel pipeline data path. So, after every cycle you will get some output for a data. So, it will be 8 bit per cycle, and your timing is something maximum of this combinational delay. Okay. So, now your objective is something you try to improve your so when you are talking about your speed of your design, you try to either improve your throughput. So, it will be either high throughput or low latency, or you try to improve the timing, that means reduce the critical path delay, that means you try to improve the frequency, right. So, this is the objective of goal. So, we are going to discuss about how to improve your throughput, how to reduce your low latency, and how to improve your timing of your design. All these 3 aspects we are going to discuss. Okay. So, so as I mentioned, this is high throughput is something number of bit per coming out of the output. How to maximize this number of bit per seconds? By pipelining, right. So, as I mentioned here that so basically you have to process multiple data in parallel, what is happening here, right. So, it is not that you give input A here, it will take 3 cycle and nothing is coming in, because if your circuit demands is such a it is implemented, this part is free, you can actually process the some other part of the data. So, if you just do the pipelining, your throughput actually increases, right. So, this is something happening here. So, so basically if you do the pipelining, your throughput will increase, right. So, that is something I just discussed. The new data can begin processing before prior to data has finished, right. The previous data has finished, you can actually do the processing of the new set of data, right. So, let us take an example. Suppose you want to calculate x to the power 3, right. So, your input is x, you want to calculate x power, which is x cube, right, x into x into x, right, ax into x into x. So, you can write an iterative algorithm like this in C, right. So, for I equal to 0, I less than 3, I plus plus, out equal to x into out. So, it will just calculate ax, x square and x cube, right. After the 3 iterations, you will get the results out equal to x cube, right. Your out will be x cube, right. This is something in the iterative algorithm, and its equivalent hardware will be like this. So, you have these registers, this is out, and you calculate. So, initially you just store this. So, when your start signal comes, you store x here, and you just multiply this x into out. So, initially this is set to 1. So, this has a set signal and it is set to 1 initially, and you just multiply and you store this back, right. You just store this back to the register. So, after start this x will come, first it will x, then x square, because x into 1 initially it is going to happen x in the first clock it is x into 1, because x is going here, right. So, x is going here and this is 1. Then in the next clock this, so that this is will store back to this. So, x into x, right, and then this is, so it will become x square, and then you multiply again x. So, it will become x cube, right. So, this is how this is the iterative algorithm works, and it needs 3 clock cycle, right, 3 clocks to complete this, right. So, this is something iterative algorithm, and I just remove the other signal just to make the circuit a little bit simpler, because it since in 3 cycle you need some finish signal, right. So, you need some, it has to some finish signal that my data is ready now, or you need the counter, that n count, which is actually counting this 3 times, 3 iterations. So, those I have omitted, but those will be added, but the basic idea of this design is that I can actually do it iteratively, and I can do it in 3 cycle, right. So, this is something, and what will be the throughput of this design? Since I am actually and this is something, it needs 3 cycle to process one data, right. If you just give one x, it needs 3 clock, then it will finish, then you can only give the next set of data, right. So, if you just give a here, then clock 1, 2 and 3, you will just process a, right, and then you have to in clock 4 you have to give b, contrary to the previous design where I give these things in all parallel, right. So, in every clock I am giving a new input a, b, c, d, e, f, but in this design I have to give a and you have to wait for 3 cycle, because this will need 3 cycle to compute a cube. Then you give b here, and again you wait for clock 4, 5 and 6 to compute b cube, then you give this, right. So, this basically in every 3 cycle you are going to produce one data, right. So, your throughput will be 8 by 3, right, because I assume my output, I mean all data path is 8 bits, and latency is also 3 clocks cycle, because this registers, though even it is a register 1, but effectively you can see that my data is processed 3 times. So, it is going through the same register 3 times, so latency is 3 clocks cycles, right, and the delay of this register things is maximum 1 multiplier followed by this mux. So, the maximum timing is determined by the delay of 1 mux and the delay of a multiplier, right. So, this is something, if we just implement a iterative version of this algorithm similar to the C code, you will get this, right. But as I discussed the pipeline version in the previous cycle, you can have a pipeline version of this design, where I actually use 2 multipliers similar to my previous design. This, so this is now a multiplier, right. You can think about this is my multiplier, right. So, this combination is just not a multiplier. So, you can just, so this is that version. So, I have this x, I am just multiplying this. So, here it will always become x square, here this is x square and this is x. So, this will become x cube. So, x cube will be the output. So, it is doing the same thing, but I am just making it pipeline variant, right. So, I just pipeline the whole design, and here you can see that as I mentioned earlier also, after first 3 clock of the, after 3 clock only the first data will come, but after every cycle you will get one output. So, your throughput will be 8 bit per clock, your latency is 3 set of registers. So, it does not change the latency, and the delay of is something 1 multiplier, right. So, delay of 1 multiplier, because here also there is a multiplier, there is also multiplier. So, the delay of this particular circuit will be 1 multiplier, delay of 1 multiplier, right. So, what happened here, from this 2.7 bit per second per clock to I make it 8 bit per clock. So, I improve the throughput of the design by just pipelining. So, pipelining is kind of a technique which actually improve the throughput of a design, right. So, if you just do this, but here you can understand. So, what is happening here is that x square and x cube calculation is coming in parallel for a given input, right. So, that is the important factor, but the resource resource increases, right. So, earlier I just used one multiplier, I am now using two multiplier, right. So, basically the number of earlier I was using one multiplier and one register, now I have three registers and two multiplier. So, the resource is going in proportion to the increase in proportion with this factor, right, the rolling factor, pipeline factor. So, will be determined with this. So, if your throughput improves by say n times, your area going to be increased by n times also, right, in proportional to n times, some n times. So, but most likely there is no change in latency and timing, right. So, this is mostly remains same. But so, basically you understand that if you want to improve your theory, I mean throughput of your design, your area will also increase, but if you do not care about your area because your design is small, even if it takes more area, it does not matter for you because your design is small. So, in that case you can, if you want to improve your throughput, this pipelining can be an approach which is actually you can apply to your design, right. So, this is one way of doing this, but you have to keep in mind if your design is very big and area increment is not something is acceptable for your design, then probably you cannot just apply this kind of technique. So, all depends on your target architecture, target designs, target design size, requirement and right. So, you cannot actually do all this, you cannot improve your throughput, you cannot improve your timing and improve your latency all at same, improve your latency in the same time. Either you have to improve throughput in the expense of latency or expense of area, or if you want to reduce the latency in expense of timing, decreasing the timing or even decreasing the throughput, or if you want to improve your timing with the expense of little bit of extra area and throughput, right. So, this is something is always there. So, there is a trade off and it depends on your design choice which one you are going to choose. Okay. So, we are discuss about this high throughput which is a pipeline implementation, you can achieve that. Now, I am going to talk about the low latency one. So, in your design, so low latency means what? So, you try to reduce the number of register level in your design. So, it is basically just removing some register, right. Pipeline register, you just remove some parallel pipeline, remove some register from this pipeline stages, right. So, this is something you just do. So, for example, in the previous design I have a register here, I have a register here. So, I just remove this register, I have just removed this register. If you just see this figure, I just remove this register, I can remove this register, then all these things are working in parallel, right. So, this is what I have done. So, here all these things still my throughput is 8 bit per second, because every clock I am going to get output latency is reduced from 3 clock to 1 clock, because now if you give one input in 1 clock, whole things are done in same clock and the output will be available in 1 clock itself, right. But your combinational delay is increased now, 2 multipliers. Earlier it was only one multiplier because there is a pipeline stages here. Now, I have 2 multiplied in a path, which is improve and decrease your timing by a factor of 2. Earlier, if you are achieving 100 megahertz, you are going to have to achieve now 50 megahertz, because you are now there are 2 multiplied in series and multiplied usually a very complex design. So, your clock period will be reduced by 2, right. So, this is something is going to happen. Again, it is suppose if your primary objective is to get it latency, reduce the latency, then probably this is acceptable. But most of the time this improving timing is the important factor. Most of the design people try to, designer want to improve the timing or improve the frequency, he has to achieve more frequency rather than this throughput or latency. So, among these 3 factors, this high throughput, low latency and improved timing, timing is the most important factor, and people put maximum attention in improving the timing. So, we will discuss that timing improvement now. So, as I mentioned, this clock period or the frequency is determined by the primarily this combinational delay of that, as I mentioned here, that combinational delay of that registers, right. So, this is something is determined by this, right. So, this combinational delay. So, now we can understand that, but if you just consider the actual factor, there are multiple other factors. First factor is something clock to Q, which is basically clock time from clock arrival until data arrival. So, it is in your design maybe that clock arrives, but data is still not computed, right. So, you need some extra time. So, that is called clock arrival until data arrives, right. So, that is something clock to queue, and then logic. Logic is something the computational delay, which is we all know about the computational delay is the logic delay, computational logic delay between two flip flops, and the routing delay. So, when you physically place those two registers, right. So, if you have a register here and there is a register, they may be placed very close by in the actual IC, or they may be placed in very far, right. If it is placed very far, then there is some time to remove the which actually have the routing delay as well, because now you have to connect this two pin, right. You have output is going to this input, this might go directly like this, or it might be route like this, right. So, it might be route like this. So, because of the routing, it maybe the routing path is very high, or they may be very placed very high. So, the routing path automatically becomes very long. So, there are some time involved in routing also, and also there are some setup time of the registers. It is basically maximum time data must arrive at d before the next clock cycle. So, you need some setup time. So, the data should be stable at the input of the register before the clock comes, so that it can update it in the next rising clock, right. And then the skew is something where the clock that is, so suppose the same clock is coming here to this register as well as through these registers, but there might be some delay, right. They may not come in the same time. So, the time, the skew is something the propagation delay between the launch flip flop, this is the launch flip flop and this is the capture flip flop. So, so the time difference between its coming here versus coming here. So, that is something is the extra time you actually get in your circuit, right. So, which is that is why this is minus, right. So, this is the actual the factor actually it will determine the frequency, the maximum frequency you are going to achieve in your design. Okay. So, when you are talking about improving timing, that means you want to achieve more frequency, you try to reduce either logic or routing delay, right. So, other is mostly I mean there are other techniques to reducing skew and all those things, but primarily the primary factor we are going to talk about how to reduce the logic combinational circuit delay. We can do several kind of techniques, so that we reduce that combinational delay of between two registers, and so that this factor is reduced. And also routing time, we can do certain kind of optimization which actually improve the routing. So, we are going to discuss about how to improve these two factors, so that if this factor going down, so this will increase, right. So, this is something we are going to achieve. Okay. So, there are several techniques and very widely used techniques. One of them is retiming, and next technique is add register layers. Then we can also do the parallelize some structures, flatten logic structures, reorder paths or replication, right. So, these are the all kind of techniques that are applied to improve your timing. So, we are going to discuss them briefly. Okay. So, first we are going to talk about retiming. So, what is retiming? It is basically moving your registers in your design without changing the functionality of your design. Okay. So, you just move your register in your design, so that the combinational delay become less. Okay. But you have to keep in mind that you should not change the functionality of your design. So, it is basically move or repositions of your register in a design to improve timing, right, without violating the functionality of the design. So, let us take an example here. Suppose I have this big logic. So, this is all my combinational circuit between this register, right. These are the input set of registers, this is the output set of registers. So, there are many paths. I have one path like this is one path, this is also one path, this is another path. There are 4 paths, right, from the input to output, and all paths are involving the same set of registers. So, we can consider, so there are all paths are critical path, right. And if you assume by this addition is taking 20 nanoseconds and multiplier is taking 50 nanoseconds, and the other factor like this Q and this clock to Q, this setup time and all those things contributing 10 nanosecond. So, total delay of this critical path is 100 nanoseconds, right. So, if you have 100 nanoseconds, so you are going to achieve 1 by 100 nanosecond means 10 to the power minus 9 into 10 to the power, this is 1 second. So, this is something you are going to achieve 10 megahertz, right. So, this is something, this is you can, this is 10 to the power minus 9 into 100, right. So, this is 100 into 10 to the power minus 9, so this is 11. So, you are going to, this is 12, right, sorry, nano is 12. So, you are going to get a 10 megahertz, right. So, in this circuit you are going to get 10 megahertz, because the total delay of this circuit is 100 nanosecond. Okay. So, now how we can improve this? So, you can actually move these registers here, right. So, instead of placing this register here, you can place this register here. So then your circuit performance will increase, right. So if you just think about this, so this is my actual circuit where the maximum delay of the circuit is 100 nanosecond. Here what I did, I just moved this resistor here, right. So I just moved this resistor to here. So now what will be the maximum delay? So this is something 20, this is 20, this is 50, and there are other delays. So maximum will be 60, right, 50 plus some other factor. So there are 16 nanohertz. So you are going to achieve more clock, right, 16.7 megahertz. So this is something is called retiming. So you just move your resistor in your design so that you can break the critical path, right. So you try to reduce the critical path length, so that is something, and again you have to keep in mind that you are not going to change the functionality of your design. So there are certain factors. So how you can move? So if you can move resistors, if both the input there is a resistor, you can move it, right. So for example, if you have this, if there are resistors here and here, then only you can move it to output, right. So if you can do this, then only you can move this resistor to this output, right. If there is only one here, this is not there, then you cannot move this, right. Then the functionality will change, right. If there is only one resistor here, then you cannot move it, right, because then the functionality will change, because earlier what is happening, both input is delayed by 1 and then calculation is happening. So say output was like A, so suppose this is A and this is B and there is a resistor here. So earlier this is out equal to A t minus 1, whatever is coming in t minus 1 is going to, so this is plus and B t minus 1. And if you just remove if you just move it here, what is happening here? So you can say, okay, let me just consider this example. I have only one resistor here, and so this is what happening. Then you are actually calculating this, right, A t minus 1, whatever the t minus 1 time data comes, we are adding with the current time B t, right. T is the present time clock, right. But in this circuit is happening here. So in this case, out is calculating like out equal to A t minus 1 plus B t minus 1, right, because there is a resistor here. So the whatever the computation is coming, it will be delayed by 1. So these two are not same, right. So if you have resistor in one path, you cannot just move it to output. You can only move if there are resistor in both the input, you can then only move it to the output. Similarly, if there is output here, it has to move into both the input, right. So you cannot just move into one of the resistors. So you have to move it. So it will come here and here, you remove this, and then you can again move this to here, right. So you can move this. So that is what I have shown. So that is moved here, and this again move it to both the inputs. So this is the retimed circuit, and you can understand the earlier the delay of these 3 units. Now I have only 2 units, right. So all maximum path length is 2 units. So here is 1 units. There are 2 units here. This is 1 unit. This is 1 unit. This is 2 units. So maximum delivery is the 2 unit of this particular module. Okay. So this is how called retiming, and retiming is very widely used technique to improve your timing. So this is and this can be automated. We are going to discuss how to automate this whole process to improve your clock period of your design. So this we have a separate module to discuss that. So we will go into detail of retiming in that particular module. So I will move into the next technique, which is called adding extra resistor layer. So retiming is something you are not adding extra resistors. What you are doing, you are just moving your resistors in your design to reduce the critical path length. Okay. So here what we are doing, we are instead of moving, we are just adding some extra resistor layer, right. So if you just consider this design, so suppose I have this FIR design, what I am calculating this AX into BX1 into CX1, where this X is just shifting to X1 and X2, right. So this is something is happening here. So this is the circuit. So this is my X1, this is my X1 and this is my X2, and this X is coming here, it is storing here. So I am calculating A into X here, this B into X1 here, and then C into X2 here, right. But these three are all in parallel, and then I am just adding them up, right. So this is what I am doing here. So this is what I am doing here, right. So but the critical path length is what? I have a adder and multiplier. So all path has one multiplier and one adder, right. So the critical path length is something is like this. So what I can do, I can just add one extra resistor layer here. So that is what I have done here. So that a critical path is now the delay of the maximum of one multiplier, right. So this has this path has only one resistor adder, but this paths have one multiplier,
and usually multiplier is more complex than adder. So, the critical path will be determined by the delay of this multiplier. Okay. So, you can understand here that if you just add register, your latency will be increased by 1, right. So, but that has to be taken care of. So, it is not that if you this is something is you actually changing your functionality, but you have to synchronize your design with other component that your data will come after 1 cycle. Earlier if it is coming after 5 cycle, now it is going to take 6 cycle to compute the things, because I am just adding one extra layer, right. So, you have to just take care of that particular factor, so that you can actually synchronize your whole other you can synchronize your this part of the design with the other component of your design. Okay. So, this is something you can do, but again there are other factors that has to be taken care. Right. So, what I just say that adding register layer improve the timing by basically dividing the critical path into smaller path, but you have to basically it is improves the latency, right, increase the latency. So, obviously, it is going to increase because you are adding in your design, and it is basically it is not be affected if you have to just, but you have to be careful about this. So, when you are adding a layer, you should add in all parallel paths, right, that is what I mentioned. So, if you just add here not here, then it is a problem, right. So, suppose if you have said there are 4 parallel paths from the input to output, right. So, this is my input and this is output, and you cannot just add one register here, because this is very critical. If you want to add a register here, you have to add in all parallel path. Even if this is said there are 4 multiplier in this, right. So, if you assume that there are 4 multiplier here and this path are simpler, only I have say 1 multiplier, right. So, you just say I have to add latency, I will just add in between and I am done, then this is wrong, because now that then there is a if you just add 1 latency here, then this data will be delayed by 1, but this will all come in as earlier, right. So, then the problem what will happen, this is not synchronized. So, the idea is that when you are going to add extra latency, it has to be in the all parallel paths, even if it is not required for this path, because you need only this path, but you have to add in parallel path to keep your functionality intact of your design. So, this is the factor that has to be taken care, otherwise your functionality will differ, right. So, this is something the factor that has to be considered, and also as I mentioned that whenever you are adding this extra layer, you have to take care of this latency is increased by 1. So, you have to, if your block is synchronized with other block, that has to be taken care, right. So, these are the 2 factors you have to consider, but using adding register you can actually improve your timing, right. So, that is something is one more technique which you can consider. Okay. So, next the topic is like parallel structure. The parallel structure is something, if you are computing something in sequentially, right. So, that will be added up, right. You just do starting from there are say 4 modules and you just do this component. So, so this is on registers and this is on registers. So, the computational delay of this whole 4 unit will be added up to and which will determine your clock speed, right. But you can in certain time you can change your design as a whole. It is not like that you can do something here, you can, but you can change your logic little bit, so that you can actually parallelize these things. So, for example, you can just maybe you can do something like this here. So, that the delay will become maximum say 4 now. Okay, sorry, earlier it was 4. So, suppose you can do something so that your delay will become now 2, maximum 2, right. So, you can do certain kind of optimizations, but this is all your design choice and this is the expertise of the designer. It is not possible in all places, but certain time you can do that. So, for example, if you just take the same XSQ power 3 example, when your input is x, and now you can think about, so my x is actual input is 8 bit, but you can think about that x has 2 components. This is the 4 MSB 4 bit and LSB 4 bits, right. And you can do, and you can store this MSB 4 into register A and the lower LSB into register B, and you can do some multiplication separately, right. So, that detail I am not going into detail, we can refer some other places, but the idea is that now your x into x is nothing but these 2 component, and you can do this multiplications of the smaller unit, this is all 4 bits, right. You can do and then combine these results to get these results x square, right. So, this is possible. So, the basic idea I just try to understand, give you the notion here is that instead of doing this 8 bit multiplication, now I can do 4 bit multiplication, and all these 3 A into A, this A into A, this B A into B, this is A, this is AB and this is BB. This can be done in parallel, and these are all 4 bits. Earlier what I am doing here, so the example is so earlier what I am doing here, so you just doing a multiplication here which is 8 bit, right. Though there is you can feel I have only one multiplier, but the delay will be determined by the combinational delay of this multiplier. But now what I am doing, instead of this 8 bit multiplication, I am doing 4 bit multiplication. So, all are 4 bits, which will be the delay will be obviously less compared to this 8 bit, and I am doing all these 3 in parallel, and I just combine these 3 results to determine the output results, right. So, this is something can be done. This is just to give you the idea that in certain time some complex operation can be splitted into smaller component and smaller operations, and combining the smaller operation results can generate the actual output, and where the smaller operations can be done in parallel, right. So, this is the objective of giving this example without going into detail, right. So, this is kind of you can parallelize your structure to improve your timing. Okay. This is one more technique. The next technique I am going to discuss about is the flattened logic structure. Again, sometimes you write something without understanding how it will be finally implemented in hardware. Let us take an example like this, where you just write key if control. So, you have input say control 4 bit control, and you are actually setting some register bit based on this, right. If the control bit 0, then you are going to your input is 1 bit, right. So, you are storing this input to the 0th bit of the R out, right. If it is 1, then you are going to update this input the bit 1 of that output. Similarly, if it is control bit 2 is 1, then you are going to update the second R out 2, the third bit of the register, and similarly this if 3 the R out 3 are going to update with this, other bit will remain as it is, right. So, if you just write this is very obvious, this else if you are writing like this, right. But if you just think about what is the equivalent hardware implementation, you just look into this. So, if your control bit is this is your 0th bit. So, if it is 0, this is that 0th bit you are going to. So, you are taking this your register, this is R out, is going here. I am taking this 3 to 1 bit and the 0 bit from here, and combining this 3 to 1 bit here, 3 to 1, and combining this 0, I will update, right. So, this will basically I am taking this input directly, this is the input, the red is input. So, input is coming. So, input is the 0th bit, this is your in, and I am taking this 3 to 1 as it is, and that will determine this result. So, this is what I am doing here also, right. So, this I am just updating the 0th bit, other bit is as it is. Now, if this else is true, that is else if, that means that time control 0 is 0, right. This is 0, then only this else will be true. So, I have to now I have to add a AND gate, where I have to check this control 0 is 0, that is the negation of is 1, and I am going to check the control bit 1. If it is true, then I am going to take I am going to update the 1 bit. So, I am going to take 3 to 2, I am going to take 3 to 2 and 0 bit, and the 1 bit will be updated from this, right. So, this is the input will be the 1 bit, I am combining this to get the results, right. So, similarly, when this both is 0, control 0 is 0, control 1 is 0, then I am going to take about this control 2, right. So, if this is the case, then I have to now check control 0 bit is 0, control 1 bit is 0, and control 2 bit is 1, then only I am going to update this third bit. So, I am going to take 0 to 1 and 3 from this register, and the second bit 2 is going to updated by the input. Similarly, when I have to check when this third bit, then I have to check this 0 is control bit 0 is 0, 1 bit also 0, second bit is 0, and the third bit is 1. So, I need big adder to just to realize this, right, because this all possible combination is coming, and then I am going to just update the third bit. So, 0 to 2 I am going to take from this R out, and third bit I am going to take as the input, right. And there will be fourth case as well, that all of them are 0, right. Then you have to just copy paste, you are not going to, if this is the become the enable of the design, right. So, if this is the case, I am not going to update this data, right. So, if this is something the implementation of this circuit in hardware, right, and you can understand these are the big adder is happening here, right. So, we usually when you are writing code, we do not consider about this putting this else, but it may be the case that in your design your control can is a kind of decoder, right. So, only one bit will be 1, right, among this control 0, 1 and 3, it can have only this, right. So, this control 0, 0, 0, 1 or 0, 0, 1, 0, 0, 1, 0, 0 or 1, 0, 0. If you know this in this case, even if this is your design, so your control bit can be a kind of a decoder, only maximum at most one of the bit is 1, Then if you write this, if you write this code, this is actually generating lot of redundant extra adder, right. So, these are all big adders, unnecessary, these are unnecessary, because you know that your design is actually a maximum one of the bit is 1, and you can rewrite code is like this, right. There is no else here. So, you can see that there is no else here, and that is a big improvement in your design. So, if this control bit 0, then I am going to update 0th bit. If it is 1, then I am going to update 1 bit. If it is 2, I am going to update 2 bit, and this, right. Then the equivalent circuit will be like this, right. So, this is my this output is going here. So, this is the third bit, second bit, 1 bit, or 7th bit, and going to this control is the signal of this mux, right. If this sorry, so this would be 3, this is 2, this is 1, this is 0. Okay. So, if your third bit is 1, then he is going to choose this 1, right. So, this automatically choose the third bit as 1 put here, and all other will be the original bits, right. So, only maximum one of the bit of this register will be updated by this circuit, because my know this my controller is this is decoder. So, either the 0th bit will be updated, or the 1 bit will be updated, or second bit will be updated, or the third bit will be updated, right. So, you can understand, if you know that it is a decoder circuit and your circuit is not something that all of them will be 1, even if you write this code, this is correct, there is nothing problem, but it is generating a complex resource, and computational delay is also big, right, because you are now having this big marks versus this adder delay will also come, right, because this adder is something 4 adder, it is basically 3 adder, right. So, this is adder of 3, right. So, this all is something come into picture, and your computational delay will improve, but if you know that your circuit is like this, you can actually flatten this, and your now the delay of this only 1 mux. So, it will be improved by a lot, right. So, this is something kind of flattened logic structure, where you know that your circuit has specific type of behavior. So, you should write this kind of code instead of writing this with if else, right. So, that is something will generate complex hardware, and your timing will be can be affected by this kind of coding style. Okay. This is something we should always think about when you are actually designing a circuit, and based on the input parameters we have to write our code judiciously, so that some unoptimized hardware is not generated by the synthesis tools. Okay. So, now I am going to talk about another technique is, again this is something designer choice, is the reorder path. So, when you are writing this if else kind of code, some nested conditions, that is actually generate in the hardware a long combinational path, right. So, if you just take this example, if condition 1 I am choosing output equal to 1, if condition else if, that means condition 1 is false and condition 2 is true, and this is less than b, then I am going to do this, right, else I am going to choose this. So, if you just see the hardware, so if condition 1 is true, I am going to choose A, if condition 1 is false and condition 2 is true plus c less than 8, this is c less than 8, this 2 are both true, then this will then I am going to choose B, right. So, this become the conditions, and if this is not true, then I am going to choose C. You can see that the conventional delay of this path involve these 3 gates, right. So, this gates, and this gates. So, total delay of this path will be 3 AND gates, right. But you can actually rewrite your code little bit different manner, because you finally have to choose between A, B, C, right. So, you can rewrite such a way that these 3 can become parallel, right. If you just rewrite what I did, I just do this conditional 1 into conditional 2, and this become condition B, and I am choosing B first. So, earlier I was choosing condition A first, then B, and then C. I just do it now here, I just choose B first, and then A, and then C. And what I did here, actually I do this condition 2 and condition 1 versus this C less than 8 in parallel, right. So, you just see the circuit, I am checking condition 1 is not true plus condition 2, and I am in parallel I am checking C less than 8, and then I am combining these 2, right. So, this and this, then I am choosing B. So, I am doing the same operation as this design, but my delay of now actually I have maximum 2 AND gates, right, which is less than the of the previous circuit. So, this is all called reorder path. So, it is kind of a designer choice. When you actually have a long if else structure, you should actually think about how you can reorder your this conditions, so that you can the design that critical path that is generating will be a little bit less than the little less than the previous one, right. So, I just shown the example. This is just a toy example, but if you just think about your complex logic structure, this can be really big, and you can actually parallelize these operations, separate condition check in parallel, so that you can reduce the length. Okay. This is what is all about reordering of paths. The last one I am going to talk about is the replication. What is replication? So, this all the previous techniques I talked about is just to reduce that logic delay, that is the computational logic delay. The other factor that I talked about was that routing delay, right. So, the replication is a strategy that actually helps to improve this routing delay. Okay. And what is this? So, if you just think about a high fan out node, right. So, suppose from this node there is 1000 fan outs. It is very common in design, right. When you go to logic level, when you have all this gate level, and there may be some source like clocks and all, which actually is very high fan out, things like resets pin and other pins, which actually generate very high fan outs, right, 10,000 pins, I mean fan outs. Now, you think about the placement. Finally, when you actually going to do the synthesis, all this node will be placed somewhere in the die, right. So, if there is a high fan out node like this, it is not possible to place all of them nearby places, right. This is the source, you cannot, because the resource surroundings is limited, you cannot place all this 10,000 around this source node, right. So, some of them have to place in very far, right, and that will become a long path, because there is other no choice, right. So, the sum of the path definitely is going to be very long, and the routing delay of those path will be very high. Okay. So, how we can actually improve those things, and that is what is called replication. What we can do, I can just replicate this source and I can make a multiple source, right. So, what is I just discuss here. So, I have this high fan out node source, it is going to various designs as a 10,000. I can split this, I can create multiple source one, right, and whatever the things input is coming, I just copy to all of them, and I just split these fan outs to these sources, right. So, I just split these fan outs, there are multiple here, I just split combine these two and make this fan out of this, I combine this and just make the fan out of this node, and this component I just make the fan out of this. So, maybe I just created 3 and this 10,000 can be splitted into say 3000, I just give a, so this may be say 10, you can copy to 10 copies, I just keep 3, but you can actually create 10 copies, and all of them have the less fan out now. And whenever there is a number of fan out is less, the possibility of placing those fan out nodes nearby is possible, okay, or high. So, then probably that during placement and routing, your synthesis tool is able to place those components near to this place, and the routing path or the delay of that longest path will be reduced, and which is effectively improve your timing. Okay. There is one factor here which you should, I mean I have not discussed yet, is how to club this fan out, right. So, what I just talked about, I just split this source into multiple source now, okay. And now I just say there are 10,000 fan outs, how to club, which 3000 I should put as the output of this, which 3000 I put as the output of this, and which 3000 I should put as the output of this source, right. Here I should always maintain the hierarchy of your design. It is very obvious that whenever there is a hierarchy in your design, all these nodes are a little bit connected, and the synthesis tool try to place those nodes inside a particular hierarchy in close by places. So, if you just put one hierarchy to the same source, then there is a high chance that all these things will be placed in nearby places, right. So, that is something is very important. As I will repeat again, it is like if there are say 100 component of this fan out is connected to this fan out, right. Now, if you connect all of them here to this source, and then there is a high chance this all 100 will be placed nearby places. So, then there will be no long routing path, but if you just the way you are splitting these fan outs, it may be that this is placed, this component is connected to this component is connected to this component is connected to this, then your purpose is lost. Again this same hierarchy, different component are connected to different sources, again they cannot be placed near to all sources, right. So, then some of the path will be long. So, the idea is that when you are actually splitting these fan outs, you should keep track of the hierarchy. So, that all the fan outs in the same hierarchy you place them into the same source. So, that your placement tool do not find difficulty to placing them nearby places, and as a result of that your routing delay will be improved, right. And you might ask me the same question again, if you split this, I mean create multiple source, it is not only 3, usually you do it say 1000, right, because there are 10,000, I want to make it simpler. So, I may create say instead of 3 I say 1000 source, then the source of this may become a fan out, right, high fan out node. Earlier I have only from this source I have only one fan out, now this will be giving to all this fan out. So, this become now 1000. Okay. So, this something again you have to do this this replication for this node as well. So, this is kind of a repetitive or say recursive way to do this, right. I have to apply this recursively starting from some high fan out node to his source and then his source and so on. Finally, I find out some node which is not that big. Okay. So, this is something it is kind of a we can apply during this logic synthesis, which actually improve the timing of your design. Okay. So, this is what is called replication. Okay. So, with this I am going to conclude. As I discussed today, we have discussed about several strategies which actually improve the either it is a throughput of your design or reduce the latency of your design or primarily improve the timing of your design or you achieve higher frequencies. Okay. And some of the techniques can be automated like replication, retiming, adding register layers, but some of the techniques like flattening logic structure, parallel structure or reorder path is kind of is responsible of the designer, right. So, if you find some long path, it is the choice of designer who has to do it manually to improve the circuit performance, but some of them can be done automatically and is actually implemented well in any industry level synthesis tool. So, we are going to discuss one of them in coming classes on retiming. Okay. So, thank you.